King, and I'm the innovation lead at Foster & Freeman, the application specialist at Foster & Freeman. Just a bit of housekeeping before we start. To simplify proceedings, all of the guest microphones are going to be muted during the webinar, but please feel free to ask questions using the chat box, and we'll go through as many questions as we can at the end in our Q&A forum. Today's product focus is going to be on Recover latent fingerprint technology. It's a new technology for the development of impossible fingerprints from metallic evidence types. So Recover LFT is a novel one-stage chemical fuming technique, and the process itself is probably best considered as a hybridization of iodine, superglue fuming and vacuum metal deposition in terms of its mode of action and its method of operation. Recover itself was developed through collaboration with the UK Ministry of Defence, Defence Science and Technology Laboratory, Loughborough University and Foster & Freeman. Now, Recover utilises both a conventional and a more unique development mechanism. Conventional techniques that you're used to using in the laboratory, such as powdering, superglue fuming, vacuum metal deposition, and amino acid reagents, all require a latent residue to be physically present on the exhibit in order for the development to occur. So if we consider the development of finger marks on paper surfaces using something like ninhydrin, we get a reaction between the ninhydrin and the amino acids from the fingerprint residue, which causes a colour change, and the finger marks present themselves as a purple deposit. Now, although Recover works in a similar way, the unique mechanism which Recover also employs means that the evidence does not necessarily require the latent residue to be physically present on the surface. In these instances, the process relies on the presence of a corrosion signature which is induced by the fingerprint sweat on the reactive metal surface, and we get development as a function of differences in surface energies and oxidation states on the metal surface itself. That means that the technology becomes applicable to both cold case review and older exhibits that may yet have been processed. Work that we've done recently has shown that Recover works very well on evidence which has been previously processed with conventional techniques, and also evidence shows that the technique is non-destructive to DNA. In terms of the mechanisms at play, if we consider the conventional mechanism first, and what you can see on the screen is a cross-section of finger mark ridges sitting on top of a metal surface. If we introduce our reactive vapour that we generate in the Recover chamber, which is indicated by the blue circles, the vapour absorbs into the finger mark ridges, polymerises in situ, and we get development, and the finger marks appear as a dark blue-black deposit. The unique Recover mechanism, in this instance, we have the finger mark sitting on the metal surface, and as a function of time, we get reactivity between the finger mark residue and the metal surface, as indicated by the orange deposit. If we now remove the finger mark residue itself from the metal surface, we have a clean metal surface which, using traditional processes, would yield no finger mark development. However, given the reactivity of the vapour within the Recover chamber, the difference in surface energy and oxidation state induces the polymerization of the vapour directly over the corroded areas, or the corrosion signature. Given what we know about the development mechanisms at play with Recover, we can start to consider the typical evidence types that are suitable for processing within the chamber. So things like bullets and cartridge casings, that's fired and unfired ammunition types, knives and metal blades, metals that have been washed clean, whether that be deliberately washed clean to remove biological traces, or accidentally washed clean, i.e. evidence that's been discarded in a body of water, a lake or a river, for example, or evidence that's been recovered from an outdoor environment that's been subjected to rain. And also metals that have been subjected to heat. So this could be something from an arson scene, evidence in a very hot climate, or fired ammunition casings, IED fragments, whereby the actual act of the percussion and the explosion causes a significant amount of heat to be dissipated across the evidence itself. Now, we've done a lot of in-house testing at Foster & Freeman as we've been developing the Recover technology. And one example that I want to discuss here is the recovery of finger marks from knife blades that have been placed onto the knife blades as both bloodied finger marks and latent finger marks. So in this example, we placed some marks onto several knives. One side had bloodied finger marks, the other side were truly latent marks. They were left for about 45 minutes before being placed into the pond at the front of the building, where they were left for about 10 days in situ before being recovered from the pond, allowed to dry, and then processed in the Recover chamber and imaged using our DCS-5. And these were typical of the results that we were able to achieve. And this is viewed using standard white light illumination. In terms of ammunition, in 2018 at the Western States IAI, we went to a gun range in Las Vegas and we prepared some pseudo-operational evidence types. So we took 3 handguns with 3 different ammunition types, placed finger marks on them, loaded them into the magazine, waited for about half an hour before firing, and then we recovered as many of the spent casings as we could before packing them up and processing them in the Recover system. We then imaged them using white light or coaxial illumination and our cylindrical surface unwrapper, and these are some of the results that we were able to obtain. Of course, in-house trials are one thing, but customer casework and feedback are another. We've been all over the world looking at customer samples and processing real casework. Unfortunately, we can't talk too much about some of the successes that we've had due to casework confidentiality. But at the moment, we've obtained 2 identifications over in the US on fired ammunition casings from murder investigations. And the example that we've got on the screen at the minute is a piece of evidence that was recovered from an outdoor environment. There was a handgun that was found buried underneath some soil, and it was believed to have been there for about 6 weeks. The evidence was taken back to the laboratory and processed using cyanoacrylate and powder suspension, and no finger marks were obtained. When we visited this customer site, they asked if we would mind processing the handgun and the magazine in the Recover system. So we did so, and after about an hour's worth of development time, we were able to clearly see 2 finger marks present on the magazine, which obviously weren't developed using the conventional technologies that they had at their disposal. So we mentioned a little bit about imaging, but imaging is really important in terms of maximising the visualisation of finger marks that are developed using Recover. Fundamentally, the marks are visible to the naked eye, but there are instances where we need to go beyond the visible spectrum to really maximise and optimise the recovery of our finger marks. One thing that we have learned is that what we can see visibly isn't necessarily all that's there. So this example, which we've got on the screen at the minute, shows a finger mark that was developed using Recover on a sheet of bronze. And the image on the left is what's seen by the naked eye in terms of direct illumination, and we can see the contact area where the finger mark has been developed on the bronze plate. However, it's not until we look at it under coaxial illumination or episcopic illumination that we really start to see the level 3 ridge detail within the finger mark. If we move on to looking at some other metallic evidence types that are suitable, things like aluminium foil, SIM cards, and the metallic part of a USB storage device. And of course, if we move outside of the visible spectrum and we consider a shorter wavelength, so 365 nanometers, that's long wave ultraviolet, it's a lot safer for DNA. And we've done a lot of work over the last 18 months looking at ultraviolet reflection imaging at 365 nanometers. Fundamentally and primarily for looking at cyanoacrylate. However, the way that the polymer deposits following Recover processing is very similar to cyanoacrylate in so much as it's a 3-dimensional structure, and that means that it scatters the UV light quite significantly, which often means that we can get increased contrast between the developed finger mark and the background itself. Now, on the subject of 365 nanometer UV reflection background, we've started doing a lot of work looking at the impact of Recover on DNA and DNA processing both prior to and post treatment. And there's going to be work that's going to be published later this year, but the results seem to indicate that Recover is non-detrimental or non-damaging to DNA. If we move to the other end of the spectrum, so we're now considering the near infrared, so we're on a slightly longer wavelength, we've also seen that in some cases and on some evidence types there is benefit to actually using near infrared reflection imaging to create more contrast between finger mark and metal evidence itself. So we've given a brief overview on the technology, the process, discussed a little bit how the actual development mechanism works. So now it's time to actually look at the instrument and get hands-on with Recover. So this is the Recover LFT instrument. It's a small footprint system with an integrated vacuum pump beneath the main development chamber. If we look at the front of the instrument, the entire process and the technology itself is controlled by the touchscreen colour interface at the front. Above that we have the glass development chamber, and to the rear of the development chamber we have a high clarity mirror. This combination allows for full 360 degree visibility of the evidence at all times. Above the development chamber is the removable lid. And the ability to remove the lid means that we can interchange our development chamber between the standard chamber size which you see on the screen and the larger chamber, which is double the working volume. If we turn the instrument to the side, we'll see the integrated carry handles which allow the instrument to be easily manoeuvred. To the rear of the instrument we have the power socket, an interlock safety key. Below that is the USB interface whereby we can connect a USB cable to allow for software, firmware updates and also data transfer between the audit logs on the system and a USB key. Below that is the filter housing, which comprises a 4-part or 4-component chemical filter to protect the vacuum pump itself. If we power the instrument on, we're greeted by the home screen. Simple tap of the home screen puts us into the control panel window, and now we're going to talk about how we would go about loading the chamber in order to process some evidence. So if we start by talking about the evidence rack itself, the evidence rack is multifunctional and versatile. Its height can be adjusted by screwing on extra leg sections. On the top of the rack we have some slots that can accommodate knife blades of various diameter. We can also screw in some ammunition pegs around the circumference that allow fired ammunition to be placed on top. And we also have some evidence hanging clips to allow smaller evidence types, IED fragments, SIM cards, etc., to be placed on the evidence rack. Once we've loaded our evidence, the next step is to take the actual chemical, develop. These come in pre-weighed, pre-charged measures in 4 different quantities dependent on the chamber size and the evidence type that's being developed. The first step is to remove the lid and place the vial inside the chamber into the heating stage. We then lower the evidence rack into place, place the lid on, and using the motorized column lower it into place. We'll now go through the software interface using our simulator to show you how a typical run progresses. With the evidence in place and the lid lowered, the first thing that we need to do on the touch screen interface is select which evidence type we're actually processing within the chamber. So one of the things that we recommend when processing metallic evidence type within Recover is that we segregate copper-based metals, so that's copper, brass and bronze, into one set of evidence for processing, and then we separately process silver-coloured evidence, so that's aluminium, nickel, zinc, etc. So in this case we've got some brass cartridge casings in our chamber, so we tell the system that we're using copper-based metal. We've got the small chamber selected, so again we tell it that we're using the small chamber, and it would tell us which of the developed precursors to use. So in this case, because we're treating copper-based evidence in a small chamber, we need to use developer 1. If, however, we change it to a large chamber, you'll see that we now change to developer 3. Similarly, if we change to silver colour metal in a large chamber, it's developer 4, etc., etc. So if we put that back to what we've got set up here, the lid control obviously just allows the lid to go up and down. Once the play button is illuminated white, it means that we can actually proceed with the processing. So we hit that. In this instance, it's asking us if we want to overwrite previous logs that are stored within the system. So we can say yes. So the first thing that it goes through is an initializing. This is basically a safety check and checking that all of the valves and the pump and everything within the system are performing correctly. This is approximately a 2-minute process. The system then moves on to what we call chamber conditioning. This is where the system creates the vacuum within the chamber and gets the chamber and everything, the peripherals, all ready for the actual fuming stage. At this point, the process will pause and we will hear an audible beep, and the system will prompt us that we are ready to fume. You'll notice in red at the bottom the warning that a fume hood must be active before continuing. So at this point the user then initiates the fuming cycle by hitting the play button, and we enter the fuming in progress screen. There's an elapsed time counter which progresses on the bottom right, and we monitor the fuming of the evidence in real time. Typically for copper-based exhibits, the finger mark enhancement is usually seen within about 5 to maybe 8-9 minutes. Certainly no longer than about 20 minutes. For silver-coloured evidence, it typically takes longer than half an hour, up until several hours, depending on the evidence that we're looking at. Once we're happy with the fuming of our evidence, we can hit the end fuming button. Again, it will prompt us, do we want to stop the fuming process? So in this case, we'll say yes. And at this stage, it goes through a chamber purge. This is approximately a 10-minute cycle whereby the vapours which filled the chamber are now evacuated through the filters within the fume hood, and the lid raises to the end position and the system prompts us to remove our evidence. We can at this stage control the lid itself to help us allow us to remove the evidence, and if we hit the home button, it takes us back to the start screen whereby we can start the next process accordingly. A couple of things just to mention quickly on here. We have a settings window which allows us to change some of the aesthetics within the actual software, and it allows us to do things like look at our tuning cycle, which we'll talk about in due course. The system has several language formats already built into it, and of course we can set our date and time accordingly. The final thing to mention, and as you saw the prompt about overwriting audit logs, is that on the right hand side we can actually the system will store up to 64 cycles in its memory. And if we look at these, it will basically just tell us various bits of information which are important in terms of ISO regulations and satisfying sort of UCAS 17025, 17020, in terms of has the process been successful, what metal type was being used, what chamber was being used, and of course what was the actual developed charge that we were using within the run. We can export this information via the USB interface on the rear of the system, and we can also of course delete some of the logs accordingly. So following the fuming cycle, the system presents itself as you can see here, with the lid raised to the upper as you can see here, with the lid raised to the uppermost limit. The first thing that we do in order to clean the chamber down is to remove our evidence rack, and the evidence can then go off for imaging. In terms of actually cleaning the chamber, the first step is to take the glass vial from the chamber heating stage itself, place the plastic lid back on it, and discard the vial as non-hazardous glass waste. We can then remove the glass chamber itself, and using an alcohol wipe, simply wipe the internal surfaces of the chamber to remove any residue build-up that may have deposited. Using the same alcohol wipe, we can clean the base of the instrument, detach the lid from the column, and wipe the lid clean as well. Then by reassembling in the reverse order, we can start another treatment cycle. In terms of less routine maintenance steps, we may often have to replace the gaskets on the system. There are two gasket seals, one at the top and one on the base. And the spares and accessories kit comes with some spare seals and some applicator grease to allow the end user to simply change the seals themselves. The 4-part chemical filter on the rear of the instrument has a filter health monitor within the software, and is typically good for up to 100 cycles before needing to be replaced. We recommend an annual service with the instrument, and within that all internal components are checked and replaced where necessary, and importantly the vacuum pump is serviced entirely to maintain and ensure optimal performance.